this type of question I rarely get here, which is a question about using BloodHound's fuzzy logic capabilities here, right? So if you look at the output here, you'll notice that there's partial, right? There's a partial output here, and only some of these outputs, have a racing stripe, right? And basically, the racing stripe denotes a trade signal here, right? So yeah, so with BloodHound's output, you'll notice that, right, there's a red line and a green line, and whenever the output exceeds those lines, that is considered a signal there, right? And so this gentleman here is using, BloodHound's fuzzy logic to generate signals. And to summarize, what he wants to do here is when a signal comes to an end, so we can see like right here in the middle of the chart, right, there's a whole bunch of bars with signals. So Raven, and or Blackbird, will enter the trade on the first bar of the signal, right? And what this gentleman wants to do is when the signals come to an end, so like right here on this green bar, right, there's no more short signals. And so when there's no more short signals, he would like to generate an exit signal, right? So as we can see here, exit signal, and he's pointing it over here to the bar after the entry signals come to an end, right? And let's see here, I think, yeah, here we go. So for some long signals, right, the first green long signal is the entry signal. And actually, all of these are entry signals, right? So these are all the entry signals. So one thing to be mindful of. But then on the first bar where there is no signal, he wants to generate an exit signal. Right? Yeah, so one thing to be mindful here is, he has this labeled as the entry signal, right? So the first bar with a signal is the entry, right? Now, I guess, one thing I want to illustrate to people that, I'll talk in terms of Raven, but the same thing applies to Blackbird as well, for both Raven and Blackbird, which is every entry signal, is an entry signal. However, if you have a position open, Raven and Blackbird will not keep adding on new positions just because there's another entry signal, right? So once Raven or Blackbird has opened a position, right, has a trade on, it's not going to keep adding to that just because there's more entry signals, right? Basically, almost no trader wants that type of behavior, right? They want to open a position once, keep that position on until either the profit target or the stop loss is hit, right? So Raven and Blackbird are specifically designed to ignore additional entry signals if it has a position open already, right? So with that understanding, let's just say, right, so we get to this first bar here, and so Raven opens a position. Now, if there's a profit target down here, so let's say, right here where my cursor's at, you have a profit target. So, right, so this third bar down, your profit target's hit, and now your position is flat, right? So this is let's just say this is a very simple, one profit target, trade system here. So your profit target is hit down here. And so now, halfway through this bar, the position is flat, right? So Raven doesn't have a position open anymore. Well, so on the next bar, this next bar here where my cursor's at, right? Well, we can see there's another entry signal. So Raven will now open another short position. This third bar here in the middle, right? Since the target was hit, And if the position goes flat, then when this bar closes, right, there is no position on. So, so when the next bar opens, right, Raven and Blackbird will see that there is another entry signal here, and so it will execute, or it'll place another short trade. So just keep that in mind there. When you do have multiple entry signals like this, if your targets are hit, if all your targets are hit during these entry signals, right, and your position goes flat, that on the next bar, if there's a signal on the next bar, that a new, but another short position would be entered onto, right? So, okay. Anyway, so that's just a little understanding of, continuous multiple signals like this. But let's get back to the question at hand, which is, I guess, so the fact that, this gentleman wants to generate an exit signal, at the end of his entry signals, probably means that there is no profit target, right? He's probably going to use the exit signal to take, close the position out, and that's when you take your profits, right? Is when the signals end. So yeah, so as long as there's no profit targets with this, then this will work as expected here. So, well, actually, let me kind of clarify that as far as profit targets. So, maybe there's two contracts are being traded, and so you might want to take one of those contracts off a little early, take a little profit early, and then the second contract becomes a runner, so to speak, and that runner gets closed out using the exit signal, right? So that would be a typical way of using, some kind of system here where you have continuous entry signals. So, all right. So first thing I need to do is kind of generate some entry signals that are similar to what we saw in that image. And I'm just going to use those stochastics here. And this will make sense here in just a moment. But let's get BloodHound open. Click on the logic tab here so we can start working on the logic board. Hit the new button there. And let's see, what should we call this? All right, something like that. So this is basically a fuzzy logic based exit signal, right? When the output goes below, 0.8 there. All right, so I need some entry signals to kind of work with here. So I'm going to use a threshold solver. Let's connect that in. All right, and for the input, let's plug in the stochastics indicator. All right, there's our stochastics. And I'm going to use the percent D plot there. Click OK. And so for my threshold, what I'm going to do, let's see here. Let's do 80 and 20. And in the middle here, I need a number in the middle. So just keep in mind, folks, with the threshold solver, you want the highest number on top, the lowest number that you're going to use on the bottom. And in the middle, you want some kind of value, some kind of threshold level somewhere in the middle between, the highest number and the lowest number. And then for an output, I'm going to do this. So if we take a look at this, so really the important thing here is not the price bars, but paying attention to BloodHound's output. So we can see here that BloodHound's output looks, basically it has the same wave form as the stochastics, right? So as the stochastics gets closer to 0.8, right, BloodHound's output gets closer to 1, right? So I'm sorry. As the stochastics gets closer to 80, BloodHound's output gets closer to 1 or 100%. And as the stochastics gets closer to 20 here, then the BloodHound output, right, the short output gets closer to 1, right? So yeah, so here as the stochastics is going down, as it hits 20, right, basically BloodHound's output hits a value of 1. But as we can see, as the stochastic goes from 50 down to 20, right, the output increases as well for the short side, right? And of course, the opposite for the long side here. So, so basically I just created myself a quick signal source here to work with so I can build exit signals, right? So the first part of building these exit signals is you do need the entire logic for your exit signals. I'm sorry, you need the entire logic for your entry signals to build your exit signals, right? So this one solver here is representing the entire logic that created these entry signals, all right? So whatever the logic was that created those entry signals, you'll have to replace this one solver here with that entire logic for your entry signals. So so really kind of the first thing you'd want to do when building your exit signals is you'd want to select your entry signal logic template, right? So the logic template for your entry signals, you'd want to select that and hit the copy button, right? So that way it makes an entire copy of your entry signal logic. And now once you have those signals with your logic, you can then begin to build your exit signals. All right, so here's my my entry signal source here. And so the next step, now we can start building the exit logic here. So to do this, I'm going to need to use the relational, the programmer node here. So this guy does not get a lot of use, but when it does, it definitely comes in very handy here. Now, it's called the relational node because what it does is it does all these comparisons, right? It checks all of these relationships between input A and input B. So if we zoom in here, right, we can see there's an input A and an input B. And so we can do all of these types of comparisons here. There's even a very simple math formula. You can do A minus B, B minus A, or the absolute of A minus B, as well. This is by excuse me. This is by no means a math formula or a math solver. All right, you can see that it only has a 3 basic subtraction math formulas here, but it so the bigger point of this relational node is to do comparisons here, between the two inputs. And so the bigger thing to kind of wrap your mind around here is that the long side and the short side are 2 separate calculations here. Right, so we are dealing with BloodHound's fuzzy logic here. So so let's let me open up the indicator window here for a moment. So keep in mind, right, that there is a short plot and there is a long plot, right? These are 2 separate plots. And so these are 2 separate calculations, right? So what that means to the relational node is that, if I plug something into A here, right? So I plugged, this solver into A, and let's zoom out a little bit, right? So we're looking at the output for A. So keep in mind that, right, this solver, it's doing one calculation for the long output and a separate calculation for the short output. And so the relational node is not just doing one comparison. It's not just saying, is A greater than B, because there's two calculations going on. So the relational node is always doing two comparisons. So when it says A greater than B, it's going to compare the long side of A to the long output of B, right? So remember this has two inputs, A and B. So the input for A, it's going to compare the long output for the input of A to the long output for the input of B. So, it's kind of, I guess, yeah, what some people are thinking, that for some reason that this relational solver is going to compare the long side to the short side. So if they plug another solver in here, they're going to, they're thinking that when A greater than B, they're thinking that, well, it's going to compare the long output of A to the short output of B. But no, this node is only comparing the long output of A to the long output of B. And then, of course, it's comparing the short output of A to the short output going into B here. Right. So, yeah, so if you're working with fuzzy logic, yeah, just keep in mind, right, that the long and the short are two separate calculations, and they're never compared to each other, right? The long output is never compared to the short output. So there are ways of doing that, but that has to be a deliberate action. In order to be able to compare the long output to the short output, that has to be a deliberate action, that you do with your solvers here. But otherwise, with every solver here, I guess let's take the logic nodes here, right? The AND node, right? When the AND node's only comparing the long output with the long output and the short output with the short output, right? That's basically how all of these function nodes and all of these logic nodes operate. So, okay. So anyways, that's just a little extra side information, just to make sure that everyone is understanding what is actually being compared when we say is A greater than B here, right? So, but what we're actually going to want is we want to know when A is less than B, right? So remember our entry signal. So remember this threshold solver represents our entry signal values, right? That's our entry signal logic. And so that's going into A. And so what needs to go into B is we need to, we need to know when the output is less than 0.8, right? So remember those lines down here? So let me mark all the bars here, right, where we actually have an output here, right? So those are the bars that actually are generating a racing stripe, right, or a signal there. Or in other words, what I'm marking is whenever the output is greater than 0.8, right? That's what denotes a signal here when using the fuzzy logic. So I'm just going to mark all of these. Yeah, so we need to compare, the output of our entry signal to this 0.8 value. With the relational node, A is going to be our entry signal source, and B, well, I need B to be this 0.8 value, right? This 0.8. That's how I can tell, is A, the entry signals, less than B, and we want B to be that 0.8. So to get that 0.8, what I'm going to do is, let's see, I'm going to grab another threshold solver here. Let's connect this in here. And we'll just call this, 0.8 output. And I'm just going to use the SMA indicator for this, right? And the reason why the SMA works for this is if you put, the SMA on your chart, right, the plot value of the SMA is always going to be greater than 0, right? So I'm going to leave my threshold values at 0, right? And so moving averages always have a value greater than 0. So that means that the solver is always going to have an output value, right? And actually, let me do something here. Let me lock the scaling. There we go. Right there. So I've locked the scaling here. So if we take a look at our 0.8 output, right? When we look at the output here, you'll notice, and let's slide that over, right? Remember, we can see the lines here, the 0.8 lines, right? The red one and the green one. And we can see that the output, right, is stopping exactly on 0.8. And the reason why is because for the long output, I put in 0.8 instead of 1, right? So normally, you're going to want to put 1 in here. But for our special unique case, I need a way for our relational node to compare our signal, our fuzzy logic entry signal, to that 0.8 value. So that's why I've set this solver here to output a maximum value of 0.8. Right? So again, let's take a look at this threshold solver here, right? Normally you want your output to be 1, but but our little 0.8 solver, we left the value at that. So now our SMA, right? Our SMA always has a value greater than 0 here, right? So if we read the output, it says greater than A, right? Is the SMA output or value, is the value of the SMA going to be greater than A? And if A is left at 0, then yes, right? Your moving average is always going to be greater than 0. So, right, so our two outputs are like that. So now if I connect that in to the relational node, right? And so now, there we go. Let's take a look at this. So we can see, right, whenever our entry signals, right, the entry signals are going into A, and so whenever let me grab this. So whenever the entry signals are less than B, and B is our 0.8 value, then we're going to get an output here. So we can see, right? Remember, I marked the bars here that generated a entry signal, and so whenever there's no entry signal, we're now getting an output here. So now we just need to clean this up here. And first, I guess we need to understand, what output do we need for an exit signal? So let's take a look at our entry signals here. Right. So if our entry signals are short, then to exit a short trade, we actually need a long entry signal, right? We need a long entry signal, or we need a long signal. I'm sorry, not entry, but we need a long signal to act as an exit for a short trade, right? And so over here, right, if we have long entry signals going on or long trades, then we need a short signal to be an exit for a long trade, right? So a signal in the opposite direction is what we need for an exit signal, right? And yeah, so let's just take a quick look. Where does this exit signal come into play? Well, we'll just quickly take a look at the strategies here, right? So let's open up the strategies window, and we'll just take a look at Raven here. So for Raven, right, we can see here we have entry logic and we have exit logic, right? So the exit logic is where your exit signals are placed, right? So you load your exit signals into the exit logic there. So yeah, so that's what that's for. All right, so let's cancel that. All right, so we know now what type of signal direction we need for our exits. So let me just mark a couple more of these. So there we go. Right. So if we take a look at this, actually I need to move my arrows out of the way so we can actually see them. There we go. Those up. All right. It can be kind of tricky trying to get those in the right spot. All right, there we go. Good enough. Yeah. All right, let me just place another arrow. There we go. All right, so here, yeah, remember here we had short entry signals. So we need a long signal here as our exit, but we can see that right here, we have a bunch of long signals, right? And so we don't, obviously we don't want exit signals when we have short entry signals, right? Those would interfere with each other. So we need to get rid of, let me mark this, I like to use a triangle. So we need to get rid of these long signals here so that these exit signals don't interfere with our entry signals here. So to do that, right, actually, I guess, yeah, let me just kind of show that what we do want to keep are, we want to keep the bars here where there's long and short together. And let's move that over. There we go. Right. So whenever there's a single output, like a long only or a short only, we want to get rid of those. And we can see that in between the entry signals that are exits, we have a long and a short at the same time. So that's what we want to keep, right? We want to keep, all the outputs where we have long and short together. Right? And so to do that, I can use the long short modifier. And it's time to zoom out a little bit. All right, and with the long short modifier, what I can use is the product, right? Product is multiplication. And so with that, right, now we're left with what we want. Right, so again, remember I've got the white little rectangles here representing the entry signals. And so in between the entry signals, we want exit signals. Right? So there we have it. So simply put, those are our entry signals. It's really kind of boiled down to, a very simple, logic here. It just took one extra solver here to create our 0.8 value. And then with the relational node and the look back node, And our look back node is doing a multiplication function, right? And so why, why did the long short modifier here, why did it get rid of, uh, these signals here? Why did it get rid of these longs? And why did it get rid of these shorts? And, again, it got rid of these longs. So why did it get rid of that output here? Well, let's take a look at let's take a look at what's going into the long short modifier, right? And so the long short modifier is set to product multiplication. So this is one of those rare cases where the long output and the short output are actually combined together to perform a function here. And so the product, being multiplication, oops, I'll put it back on product there. What the long short modifier is doing is it is multiplying the long output to the short output, right? It's actually, yeah, so it is multiplying the long output and the short output together in product mode. And so if we think about this, what's the value of the short output? Well, it's 0, right? There is no short output. The output is 0. So 0 times anything is 0, right? So that's how the short output is removed because, right, 0 times anything is 0. So, right, so yeah, so that's how we strip out the output when it's only one side or the other, like so. And quite actually, yeah, quite a few of the long short modifier modes do actually take the long and the short output and do a function together with them, right? Most of them do. So, such as like the math ones, right? Because if you think about it, right, the long short modifier only has one input. So if the function requires, two inputs or two variables, then it's going to be using the long, it's going to be combining the long and the short output together. So like addition, right? It's going to add the long output to the short output. Difference, another math formula. Division, right? Some of these others like average, let's see, actually, yeah, the average also, it's taking an average of the long and short output together here. So some of them don't, like swap, just simply, swaps the outputs. You can mirror the long side or mirror the short side. But in this simple case, we just need the product. And that's how we're able to strip out the other side there. All right, well, we are done answering this question. This is it. So again, just a summary here, right? This one solver here is representing the entire entry signal logic. So within our exit signal, we need the entire entry signal logic here. And then we just add these 3 other solvers here, and we can generate the exit signals, as expected here. So, and I guess we might as well just discuss here quickly that, it's okay that we have a long and a short for our exit signals, right? So again, if we look at our little rectangles here, right? So if we're in a short trade here, then this long output for the exit signal, it's not going to be used as an entry. So remember, these are exits. So these will never enter a trade. Right? So again, going back to our strategy here, if we go back into our strategy, let's pull up Raven again, right? So whatever signals you put into the exit logic, as it says, exit logic. So those are never going to enter a trade, right? So it doesn't matter at all that we have a long and a short output for exit signals. So, yeah, all right. So just one little extra piece of information there. Okay, so with that, guys, I'm talked about and gone as far as I can with this question here with all the little extra pieces of information I could think of.